Now it's time for a joint talk by Kyznietsova Iryna and Soroka Yuliia. Are you here?
Yes.
Perfect. They will talk about geometric interpretation of first Betti numbers of orbits of smooth functions.
Thank you. I'm from Institute of Mathematics in Kiev, and my work is joint with Yulia Soroka. It is actually partially based on our previous joint work with her on first Betti numbers of orbits of smooth functions. And we also appreciate the help of Sergei Maximenko, who helped us a lot and consult with much attention. I start with the definition of class of functions we'll be working with. So let M be a compact connected surface and P be a real line or a circle. And we denote by F and P the space of smooth functions F satisfying the following conditions. The first one is that function f takes constant value at the boundary and has no critical points in the boundary. And the second is that for every critical point z of f, there is a local presentation fz such that fz is a homogeneous polynomial without multiple factors. And also notice that we have the following inclusions because Morse functions satisfy the second condition with the polynomials plus minus x squared plus minus y squared. So f is a very wide class of function because Morse functions are open and everywhere dense in the space of all smooth functions. Okay, so next I introduce the stabilizers and orbits of such functions, which Sergei Maximenko already mentioned today. For closed subsets of Mx, we denote by dMx the group of C-infinity diffeomorphism of M fixed on X, and it's X on the space of smooth functions by the following rule, where it's just a composition F with H, where H is from dMx and F is a smooth function. Yes, and SFX is then the stabilizer if it's such diffeomorphisms that this composition equals to F. And orbit will be just these compositions F of H. And we also will use the notation S prime S of X, where it is the intersection of the stabilizer and the diffeomorphism from identity path component of dMx. Homotopy types of stabilizers and orbits of Morse functions were calculated in a series of papers by Sergei Maximenko, Bogdan Feshchenko, and Elena Kudryavtseva. And here is a list of some results, but there are many more, of course. And one of the results which we use is the following. So Sergei Maximenko showed that we have a precise algebraic structure of fundamental groups of orbits for the case when M is not a sphere and a torus. And actually, as he mentioned today, he also showed that orbit of F is spherical, so actually homotopy types of orbit are described just by this fundamental group. So his theorem is the following, which he already also mentioned today. So if M is a connected compact oriented surface except to sphere and to torus, and F is in FMP, then P0 of S prime FGM, which is actually isomorphic to P1 of F, is in the class B, which Sergei Maximenko use notation P today, maybe remember. So it's a minimum class of groups which satisfies the following conditions: that trivial group is inside this class, that A and B from this group, their direct product will be in this class, and for any group from this class, we have the following rest product with Z will also be in this class B. And actually we can notice that every group from this class is just obtained by trivial group with number of operations of direct product and rest product. So so it can be easily written like a word in the alphabet, which can be denoted like the symbols 1, Z, and so on. So such word we will call realization of this group in the alphabet. But notice that there are different realization for the same group. For example, we can write the realization for the same group like this. So it's different realization, but the same group. And one of the results that we get with Yuliia Soroka is the following. So we denote by beta 1 of G the number of symbols Z in that realization of a group, and denote by Z of G and GG the center and commutator subgroup of G, and the theorem is following. So for G from this class and for arbitrary realization of the group, and if this is the number of symbol Z in the presentation omega, then we prove we have the following isomorphism. So center is isomorphic to quotient group by commutator, and it is isomorphic Z in some power beta 1 omega, which is already defined like number of symbols Z in this presentation. So this means that even if that the number beta 1 of omega depends only on the group G and doesn't depend on exact realization, which can be different types. Okay, and why I talking about first Betti numbers of the orbits? Because we have also the following corollary. So if M is a connected compact oriented surface distinct from sphere and torus, F is from F and B, and G is fundamental grouplet of orbits from that class, and omega is arbitrary representation of G in this alphabet, and again beta 1 of omega is a number of symbols each in this presentation. Then the first integral homology groups H1 of Z of orbit is a free abelian group of rank beta 1 omega. So this means that beta 1 of omega is the first Betti number of orbit of F. And actually, it is just a direct consequence from well-known Gurevich theorem, which states that for every post-connected topological space X, there is such isomorphism. So we have such isomorphism, and then by Sergei Maximenko result, it is the following, which we with Yuliia Soroka prove that it's just Z in this power. So actually this number of symbol Z in the presentation of the group is actually a first Betti number of the orbit. And the second result I will be talking about is the geometric representation of such number. So now to give such representation, I introduce the concept of Chromosome graph. Consider the partition of M interconnected components of the level sets of F. And the set of elements of this partition endowed with the quotient topology. And this will be called Chromosome graph of F and denoted by gamma F. And now we need to divide some vertices of this graph in several categories. Let X be a compact surface, W will be a subset from its boundary and consists of some connected components of F and of level sets. And then we have the following sets of vertices of degree 1 of this Chromosome graph. So V and D is corresponding to non-degenerate critical points of F. With index D, it corresponds to degenerate critical points. W is just points that correspond to connected components from a subset from the boundary, and such set is the set of vertices corresponding to connected components from the X without W. So we want to give a definition which vertex is external, and in this case for the function and some submanifold of M, and again from a subset of its boundary, we will call a vertex external with respect to W if vertex is either non-degenerate or it is in dx without W. So, and all other points will be called internal. Maybe it looks somewhat difficult, but I'll then show examples and it will be easier to see. And actually now we want to divide edges of our graph on external and internal again. So here edge will be called external with respect to W if it is to some external point, and otherwise it will be internal. And one of the main also notations is that this orbit in HW is the number of orbits of the action of the stabilizer on internal edges of the graph. So the main theorem is the following. Let M be a disk or a cylinder, and F be in this class FMP. Then the number of orbits of the action of the stabilizer on internal edges will be the same as our number beta 1 of this group, which is defined only by the number of symbol Z in its realization, which actually doesn't depend on realization, but only on the group. And here W is just the boundary of disk if it is a disk, or it is S1 times 0 in case of the cylinder. Okay, so for such number, just of the symbols in the group computed for fundamental group of the orbits, we can see geometrically by the action of the stabilizer on internal edges of the graph of this function. And to understand how it works, here is the example. So this will be our function f, and you see it's on the cylinder. And we see that chronological graph of this function will be the following. So all components of level sets go just for one point. So it has this structure. And let's compute our groups and orbits. So let's first consider the case when points here are non-degenerate. So in this case, which actually was showed by Sergei Maximenko, that how exactly compute these groups. So we can tell it from just functions that it's not just in that class, but what exactly how it looks. And he proved that for such function it will be zeta times zeta. And now we look on the number of orbits of the action of stabilizer. So, but we need only internal edges. So internal edges, again, it's edges which are not corresponding to non-degenerate points. So if we here have a non-degenerate point, so these edges will be external. And again, we should take points which are in W here. So if it's a cylinder, so W is just one component of its boundary, and this edge will be also internal. So you see that, and now we should, so internal edges are only these two edges, and we look how stabilizer acts on them. But it's orbits, it's trivial here, so it's only two orbits, and we see that these numbers coincide. And we also can consider this picture with the case when points are degenerate. In this case, these edges will be internal. So so when we compute the number of orbits of stabilizer, we also include orbits of stabilizer acting on this, but it's the same orbit if and these points are on the same level. So there is diffeomorphisms that can cyclically shift the points. So in this case, our number of orbits will be 3. And again, by Sergei Maximenko's theorem, we can compute this group, and it will actually be Z rest product over true with Z times Z. So here will be 3 symbols Z, and it's again coincide with the number 3 we'll get here. Okay, and maybe one more picture to get it again. So here is a function already here on a disk, and here we again assume that these points here and here are on the same level, and these 3 also on the same level, so we could be able to shift it by diffeomorphism. And here again we considering internal edges, and if it's again all non-degenerate points, then we don't compute them, and here a number of orbits is just 3, and in this case group is also calculated, and this is just direct product of z by 3 times. So again, the number coincide. And in case of degenerate points, we again we should include these edges, and again the orbit will be one orbit here and one orbit here. So it will be this number of orbits will be 5, and again computing the group, we will have except of that we will have z rest products with z over 2, and here will be the same over 3. So again, the number of z will be 5. So this number coincides. So thank you for attention.
Perfect. Thank you, Iryna. So, are there any questions for Iryna about her talk?
So, excuse me, I wonder what is so special of the sphere and the torus that the first theorem, which has been mentioned, has to rule out these two cases. My first thought would be that this should be easier. So, because okay, the topology is let's say simpler. Exactly. So about this, it is known what happens if we consider the sphere or the torus. So has one to modify the class B in order to get the P naught, or what happens for these two particular surfaces?
Yes. Actually, for two sphere, it's still open question, but for torus is what it was calculated by Bogdan Feshchenko, and here we have the similar class, but here will be rest product over two numbers, so it will shift not. It will cyclically shift in both directions if you consider covering of a torus, like, and actually for all these surfaces, Sergei Ivanovich showed that it can be you can compute it just using the same the result for just disks and cylinder, and from such surfaces he constructed the proof for all such surfaces except to sphere and to torus.
Okay, thank you very much.
Thank you.
Thank you. Are there other questions? It doesn't seem so. So thank you, Iryna. You've been very clear. Very interesting talk.